This section is about proportions and sample proportions. So when a random variable only has two possible outcomes, so like flipping a coin, you only have heads or tails, or if you're looking at the genders, either boys or girls, you can use the sample proportion as a summary of our data. We'll let n be our sample size, and x is the number of our successes, whatever we're counting. It doesn't necessarily have to be the good thing. So p hat is equal to, so we call it p with a little hat, p hat is equal to x over n. X is your number of successes, n is your sample size. So a proportion is really just a percentage but written as a decimal. So examples of sample proportions are the proportion of people on campus who are girls, or the proportion of tires that need repairs. Before we actually find our sample, we don't know our proportion in our sample, so our sample proportion p hat is a random variable. And of course we would also have a proportion for our population, not just our sample. So in example 9.1.1, in a sample survey of 2,000 college students, we ask each student whether he feels parents put too much pressure on their children. There are 840 students who answer yes. So in our case, what would be n? N would equal 2,000. Okay, and x equals 840 kids who said yes. So what's the sample proportion of students surveyed who thinks parents put on too much pressure? Well, our sample proportion would just be x over n, or 840 out of 2,000. Which is 0.42. So that's our sample proportion, or if you want, 42%. Okay. There's another one for you to try. And now you might realize that this seems very similar to our binomial distribution. And it turns out it's because it's doing the same thing, and we can use our binomial distribution to model our number of successes. But it's actually usually easier to work with the proportion of successes and use a normal distribution, just because the math's a lot easier, especially before they had computers. So we're going to explore this applet. And in this applet, there's a bin of candy that has 50% orange pieces. And if I was to take a sample, so I have a big bin of candy, there's orange in there, and I take a sample, do you think I'd get exactly 50% orange pieces? Well, probably not, right? Every sample will be a bit different, but I'd probably get close to 50 pieces. And if I took another sample, would I get the same proportion of orange pieces? Well, no, probably not. We know every time we take a sample, we're going to get a different sample proportion. So let's go see what happens in my applet. So you can see we have a big thing of candies. The probability of orange is 0.5, or 50%. Our number of candies is going to take 25 per sample. That sounds nice. Let's draw a sample. You can see it's pulling out the candy. We put everything that's orange in one bin, everything that's not orange in the other bin. And we have a little dot here, so we got 14. That's counting the number of oranges. Let's switch the proportion since that's what we're talking about. So our proportion was about 0.56. Let's draw another sample. And you'll notice I got another sample proportion of 0.52. And I can draw another one, and I got a sample proportion, all the way down at 0.32. That's pretty surprising. I can draw another sample, another 0.52. Notice every time I draw another sample, it's putting another dot down here. So let's draw a lot of samples, and you'll notice I'm getting more dots. Now, what do you think might happen if I try, say, 1,000 samples? Notice I'm getting an interesting shape here. So all of my possible sample proportions are starting to look like a normal distribution. And if I do a few more, so we've now done 10,000, it looks quite a bit like a normal distribution. And in fact, I can click and it will overlay the normal distribution. Look how much that looks like the normal distribution. So if you have a proportion and you look at the sampling distribution for all of the possible samples, okay, all the possible sample proportions, it will look normally distributed. Let's see what happens if I start with maybe a different proportion. So let's do a proportion of 0.01. And my sample size is still 25. We'll draw 1,000 samples. Okay, notice in this case, do I really look like the normal distribution yet? I don't seem to look like the normal distribution. I seem to be a bit left skewed. But if I make my sample size bigger, let's actually start at 0.1 so it's not as noticeable. Okay, look, I'm not quite normally distributed. I don't have anything really over here. But if I make my number of candies bigger, oh hi, the candy machines will be faster. Notice I now look more like the normal distribution. And if I did this even more times, I would look more and more like the normal distribution. So if you have a bigger number of candies, okay, or a bigger sample size, you look more like the normal distribution. Okay. So coming back to our theory, every time we take a sample, we get a different sample proportion. And if we take all the possible sample proportions, we get our sampling distribution for p hat. So our sampling distribution for p hat, okay, well, let's see. Let's first start with a random sample from a large population that has a population proportion of success p. So p is for population, p hat is for our sample. Let's maybe make a note of that. So p is for population, and p hat is for the sample proportion and population proportion. Okay, let's see. So p is our population proportion. Our sampling distribution are all the possible values of our sample proportion. The shape will be approximately normal. If, remember how we had to get a big enough sample size, if n times p is at least 10 and n times 1 minus p is at least 10. You do have to check both of those. Okay. The mean of all of our possible sample proportions will just be equal to our original population proportion. And the standard deviation will be equal to the square root of p times 1 minus p over n. So again, we have this notation. P is our population proportion. P hat is our sample proportion in just one sample. The mean for p hat is our theoretical mean, or the average, for the population of all the possible sample proportions. And sigma p hat is the theoretical standard deviation for the population of all the possible sample proportions. Okay. So this is a problem for you to try, so pause it now. Okay. But I do just want to point out, so I have in this first row things that start with a p of 0.5. Notice that n equals 5, we're already pretty symmetrical. At n equals 50, we look like a normal distribution. N equals 500 looks just like a normal distribution. For p equals 0.2, I start off right skewed, but by the time I get to 50, it's looking pretty normal, and at 500, it looks really normal. P equals 0.7, we start off left skewed, but by the time we get to n equals 50, we look pretty normal. By the time we get to n equals 500, we look really normal. Okay. So just make sure here you notice that as the sample size increases, the sampling distribution, or all the possible values of our sample proportion, get closer and closer to a normal distribution, which is nice because then we can use our normal distribution to find confidence intervals and do hypothesis tests.